Hello, my name is Chris, and I'm a production engineer at Facebook London, coming here to talk to you about cgroup. Today, cgroupv2, the version 2 of cgroups, which we've been working on. Don't worry if you have no idea what I'm talking about when I say the word cgroup, by the way. Essentially, it's the thing which, if you imagine all the limits which you have in Docker and LXC and this kind of stuff, it's what provides those limits. So you have a memory limit or something like this. It's essentially the system which allows you to do that. And Docker uses this internally. It doesn't do that itself. So a little bit about me. I'm working at a team called Web Foundation. The title production engineering is kind of another non-standard title across the industry, but we do basically site reliability engineering work. So I do some kind of mix of kind of like ops work and more proactive kind of work across the site to help reliability. I've been working on cgroup version 2 and OS integration. That's my main point. I do a little bit of kernel stuff, but not much. Mostly I work on integration with systemd and RHEL and CentOS and that kind of stuff. So most of my job is dealing with web reliability at Facebook. We have over 100,000 machines, and we have a really, really small team dealing with those machines, so we need a lot of tools to make sure that we have the ability to do that. And most of my expertise is dealing with production incidents. Most of my expertise is when shit really hits the fan in production, then there are a few of us who really get called on to go and investigate, especially for me, like most of my time is spent in like GDB and like BPF stuff and that kind of stuff. So in this talk, we're going to have like a short overview of cgroupv2. If you already know what cgroup is, like if you've been in sysfs cgroup, then you already know version 1. You almost certainly don't know version 2. It's very, very new. It was added only in kernel 4.5, whereas cgroupv1 has been around since 2008 in kernel 2.624. So almost certainly that's the one you've been using if you've been using it so far. It obviously has a lot of good stuff. We've been using it for like 8 years now, and Docker uses it, LXC uses it. Basically, every single containerization solution uses it. So obviously, it has a bunch of good stuff. It also has a bunch of bad stuff. I want to go into like why not everything went to plan. Also, what cgroupv2 is doing to kind of fix that. Also, why an API break was needed, and we couldn't just like iteratively fix cgroupv1. I also want to go over kind of like what's new in cgroupv2, not only improvements, but like new features entirely. And also, since cgroupv2 is very modular, I want to go over which parts are ready for production and which parts are still kind of being worked on. So cgroup means control group. So it's essentially a system for resource management on Linux. So resource here means like CPU utilization, memory utilization, I/O utilization, these kind of things. And management means some things like limiting, throttling, accounting, basically any kind of metric or any kind of data you could gather about the resource and doing something based on that data. The way that cgroup works is essentially you have this directory, sysfs cgroup, which is inside the sysfs file system. And to create a cgroup, you do like a makedir syscall. To remove a cgroup, you do a rmdir syscall. To modify some data about the cgroup, you use like a write syscall. It's basically just how Unix works. We don't actually have any syscalls for cgroup itself. You just interact with it directly through the file system. This has like a bunch of benefits. One of them is you don't have to go write some program in C, like every time you want to interact with cgroups. You have the opportunity to interact with it basically in any language you like. Anything which can open a file and like close a file and write to a file. I think that's like the basic standards for programming language nowadays, I would pray. It basically should be fine. So you can do it in your favorite language X or whatever the new hip kids are using nowadays. So the way essentially this works is you put some processes in this group, this control group, and you do something with them. Depending on your requirements, like what you might consider a group is variable. It might be, for example, you have a service and you put some processes which make up that service. It's probably not just one service. It might like fork stuff. It might have all sorts of things which that service relies on. You put them in one cgroup and you say like set a memory limit, set some CPU limit for them, and go from there. And as I said, it provides you some files which you manipulate, and those directly interact with the kernel. Like the subsystem which provides those files, when you modify them, it directly interacts with the kernel and does what you ask. So practical uses, isolating core workload from background resourcing is like the main thing for me is at Facebook we have a bunch of core services, say for metric collection and Chef and all this kind of stuff. I care a lot about those, like I care about machines being updated by Chef, but I care far more that your web requests get served. Like if all my web requests aren't being served because Chef is taking 100% CPU, then I'm out of a fucking job. Like that's useless. So I would much rather have a system which understands I should prioritize these web requests over everything else. Yes, this other stuff is important and it should be prioritized, but we should like settle this resource contention in a reasonable way. Generally, like the concept is that we want to ensure that machines with multiple workloads, say even containers, like containers who have equal priority, don't end up overriding one another. So how does this work in cgroup 1? So this is how it looks in cgroup 1. You have like this CPU and PIDs, and you have all this like say memory. So you can limit memory, limit CPU, set the maximum number of tasks in a cgroup. And then like for example, here's an example of the PIDs hierarchy. You have a slice. A slice is just systemd terminology. It's not actually related to cgroups themselves, but systemd uses it. And essentially you have like some nesting, some hierarchy, and you can set like, say I can set only 1,000 tasks in here, and this one can only set 200, and that 200 comes out of the limits which are set for the parent. So this is essentially how it works. You have a resource. In the example I gave, it's PIDs. You have a cgroup. You can nest a cgroup. Even if the cgroups have the same name, to the kernel they're completely separate. Like the kernel doesn't give a shit that you named it foo and foo in one other. It considers them completely distinct. Lots of systems like systemd do create like one in each one, and you'll see the same name. But from the kernel's perspective, and this is really important to note, they have absolutely no relation to each other. They have nothing to do with each other. That causes a whole class of like niche problems which are kind of annoying when it comes to managing services. You can set more restrictive limits in the child, like I mentioned. So if this was say memory, and you set a limit of like say 1 GB here, you can set lower than 1 GB here, and that comes out of that eats out of this particular one. But you can have like 1 GB and 1 GB, then they just share the same resource. So limits and accounting are performed per cgroup. So for example, if this one is memory, and you set the memory limit here, it applies to PID3 and PID4. And yeah, the way you essentially get these files is you just go into the memory cgroup, you create a cgroup with makedir, or you use systemd to do it for you, and then you tell it to add the PIDs. One PID isn't exactly one cgroup per resource, literally only one. If you don't explicitly set a cgroup, then it goes to the root cgroup. In this example, say resource B, the root cgroup is just essentially unlimited. You do still get accounting, so it's not like completely useless, but it's pretty damn close. So to make it clear, this is how it looks. I know I've said this like 5 times, but you have to get this. If you don't get this, none of the rest of the presentation will make any bloody sense. You have sysfs cgroup, you have a directory, which is the resource, then you have some names, say service1 and service2, then you have some files inside where you set what you want to set. And again, even though they're both called service1, they have absolutely no relation to each other. How does this work in cgroupv2? Now, here's the bit where you see if you remember everything I just told you. So cgroupv2 has a unified hierarchy. So if you go to sysfs cgroup, the same directory, you don't see the names of the resources anymore. Previously we saw like CPU, memory, all this kind of stuff. Now we just see the names of cgroups. So when we go in there, in fact, we also see all these files. So how does it know which cgroups it's in? How does it know which resources it can control? Well, the answer is cgroups are global now, and you actually opt into the resource. So essentially it's completely inverted. Instead of having a resource and you have a cgroup hierarchy underneath the resource, you have a cgroup and you have resources which you opt into for that cgroup. So for example, if I want to do this again, like I want to have CPU for service1 set in CPU shares, I want to have memory for service1 set here, it looks more like this. So now we have, say, one cgroup here, service1, and we set in cgroup subtree control memory and CPU. So what this means essentially is you have a unified hierarchy, you have one single cgroup, you're only on one cgroup in the whole system, and that cgroup controls any attribute that you could consider about your process. It doesn't act in the same way as before, where we have to actually create a different cgroup for every single type of resource, and put a PID in each type of resource, and have a cgroup for each. So this unified hierarchy, so what's the point of this unified hierarchy? Why is it better? So it allows making kind of better decisions across resource domains. There are some kinds of operations which do not only happen on one resource domain. For example, page cache writeback is a very good example, and I'll come back to that one later. It's previously really difficult to like make decisions about what should happen. Say we're about to reach the limit on like memory or something like that. It's really difficult to make a decision on how I should mitigate that situation. Like in general, it's not possible to make that decision because you don't have any like, all of the resources are completely unaffected by each other. Like they're all considered completely separately. So you have no idea like this C group actually is a one-to-one mapping of this C group or like things like this. You can't make good decisions about that anymore. We also now do granularity at the process, not the thread level. So without a whole bunch of cooperation, it makes absolutely no sense to put one thread from your process in one C group and another thread from your process in another C group. Say, for example, you have a memory limit and you want to set a limit on one, and you want to set another, you put one in one C group and you put one in another C group, two threads from your program, they both share like most of their memory, so it makes no bloody sense. Like, you're in a situation where actually what happens is completely like not well defined at all. Like, I've spoken to people who have interacted with this code and they have no idea what happens if you do these kind of things. Like, it's just simply not well defined. Generally, like the interface, there's a way higher focus on simplicity and clarity over ultimate flexibility. Like, that is the goal here. Clarity, flexibility, make it easy to use for people. Don't put roadblocks in the way for like the sake of flexibility. And in fact, that flexibility made some kind of configurations which are pretty sensible, really difficult or impossible, which I'll go into. So, I mentioned page cache writeback a moment ago. So, shout out if you want to answer. When you write to a file in Linux, what happens? Does it go to disk immediately? Where does it go? Where? Page cache. It goes to the page cache. So what happens when I write to a file? It goes to the page cache. So I just send a bunch of dirty pages to the page cache. But from my perspective, everything went fine. I gave a write call. The write call succeeded. And I am now in the happy land where I can believe that my file is updated on disk. But it's not actually updated on disk. It's actually still in memory. So we now have two kinds of resource constraints here. We have memory. You use some amount of memory to write dirty pages into the page cache, and then afterwards you spend some time expunging them to disk when, say, for example, some unlucky other process decided he's now going to write some more dirty pages and we had to flush out because the amount of dirty pages is way too high. So how do we deal with this? Because we have the problem like the actual thing which flushed out the pages to disk or caused the pages to be flushed out to disk is not the one who wrote the pages there in the first place. And it interacts over these two different domains. It acts over I/O when we actually do the write, which is way later, and memory, which is when we actually did this thing in the first place. We actually wrote into the page cache. So now in V2 we actually have the ability to do this. In V1 there is no tracking of this. Now we can, after the fact, work out that you wrote these pages, charge these pages to you, and actually retroactively go and add them to your memory limit, or go and change them out as you go. Same for I/O. We can work out this I/O came from you, and we're going to charge it back to your C group, and it'll count towards your limit. Previously, like for some workloads, this was a non-negligible amount of their workload, and it simply was not counted at all, which is really not a good way of operating. Lots of things are quite violent in cgroup v1. So in cgroup v1, say for the memory cgroup, you had memory.limit in bytes. What happens when you reach memory.limit in bytes? You get killed. That's a pretty violent action. Like, kill-9ing a process is pretty damn violent. Like, it basically gives no opportunity for them to do anything at all. So it would be nice if instead of kill-9ing a process, we could have some kind of standardized way of saying to the process or to the memory subsystem, hey, this process is about to get killed. Do you want to go do something about that? And we can actually do that. Like, now we have, instead of having this memory.limit in bytes, we have memory.high, and what happens on memory.high is when you reach this threshold, say you set memory.high at 1G, and you set memory.max, which is another one which actually does do the kill, at say 1.5G, at 1G, when you start to do like some kind of malloc or sbreak or something like this, then we will start to force you to do direct reclaim of memory. So you will essentially be forced to scan the pages and find stuff which can be reclaimed. It acts as kind of its own throttling. Not only do you get the benefit that now we're trying to actually reclaim things, but even if you fail to reclaim stuff, we're throttling you as you go along. And in general, this means it's way easier to deal with temporary spikes. Like, you don't have to worry about a temporary spike which reaches the limit, then you get killed, and this happens over and over again. Once you spike, you do some direct reclaim, it goes down, it's fine. We also had a bunch of inconsistency in version 1. Because every resource had its own hierarchy, this kind of allowed this to happen. Like I mentioned before, when you have, say, a memory limit on 1 and then you have a child of that cgroup, then it inherits the values, but that's not always true. Like, most cgroup controllers do that, but not all. It was really hairy. And then you also had this thing like cgroup controllers which do basically exactly the same thing. For example, share-based weighting and this kind of thing had completely separate APIs, so you had to learn 2 APIs to do one thing, which was completely insane. So it was all a bit of a mess. And yeah, we tried to make it better in cgroupv2. I will not say it is definitely better, but I will leave it up to you how I'm very British, I can't say it's great. So it's at least better. So there used to be like this problem, which is iterative design is great. I'm not saying anything against iterative design, but do not use iterative design when making a kernel API. Because if you use iterative design when using a kernel API and you want to make some iterative change to some file, which many people now rely on and don't know about your change, Linus Torvalds is going to have your head. So, for example, we had memory.limit in bytes, which was in theory the limit in bytes of all memory allocations, until somebody realized it only includes basically 1 or 2 categories of memory. And then somebody worked out, oh, we also want to limit kernel memory. We also want to limit like socket buffers. We want to limit all sorts of things. Well, you can't add them to memory.limit in bytes because now people rely on the old behavior. So people added like, okay, memory.kernel memory or .kernel memory.tcp or like it's a swap memory or like all sorts of these separate limits in bytes. And this actually causes like it's now impossible to limit your memory in a reasonable way, because say you set like a limit on your socket buffers and then you have one limit for memory.limit in bytes, you have one for like your socket buffers, then you set a limit on your socket buffers. Now, like if you hit that limit, even if we have 2 gigabytes of page cache or like tons of page cache to reclaim or something like this, or even if you have totally free memory, if you hit that limit, we just kill you. We don't care. Like you used up like a few bytes over like how many socket buffers you're supposed to use, we won't kill you. Which is really not a good way of operating. So yes, this is more designed up front, and in general now we have like global limits instead of per type limits. So controls which are merged into the mainline kernel as of Linux 4.8, I think. We have I/O, which does I/O contention and I/O limiting. The memory one and the PID one, these are kind of like very critical ones from our perspective. Another very critical one which is not merged as a CPU controller. There is a big disagreement about how it should work, and yeah, there is a thread here on the Linux kernel mailing list about how this should work, and there are disagreements about like that we now have granularity on processes instead of threads, and like another thing called the internal process constraint, which is essentially where you can place processes in cgroups. It's all rather, it's either very dramatic or very boringly dramatic, depending on which side you're on. Yes, so you can find out more about that, but hopefully we'll have that merged very soon. Control is still being worked on Freezer. So Freezer was essentially, instead of like when you ran out of memory, you didn't have to like get killed. You could just freeze the whole cgroup. All the processes in the cgroup would be frozen. Then you could do something based on that. Like some process could come along and say, oh, I'll raise the limit a bit based on some context it has. Or, oh no, I don't care anymore. I'll just kill them and like go ahead, or like log it somewhere. Or it was essentially like allow somebody to do something before getting own killed. So yeah, that's still being worked on. Number one question I get when talking about cgroupv2, are we actually using it in production? Yes, if you refresh a few times on Facebook, you will probably hit a Facebook server which is running cgroupv2. We are probably the only company actually running cgroupv2's machines at any kind of scale. at this point. But that's one of the reasons I'm giving this talk, because I want to tell you it's production ready, we're using it, and it works just fine. We're running it managed with systemd. We run it on CentOS 7. You can see David Akavuka, a guy I work very closely with. He talked at systemd.conf this year, a talk called Deploying Systemd at Scale. It's a very interesting talk about our general approach to operating system management. But yeah, we run it with systemd and CentOS 7, but you don't have to. We're already getting better results on spiky workloads. I already mentioned about the memory limit stuff and the memory.high stuff. And yeah, we're generally using it for like separation of workload services, say the web server from Chef and all those background metrics collection and that kind of thing. So how can I get it? cgroup-v2 is stable since Linux 4.5. It's actually been worked on since like 2012, but it's always been in experimental. Now you have very useful command line flags, systemd.unified cgroup hierarchy equals 1, which means systemd will mount sysfs cgroup as cgroup-v2, which is very, very useful. You also have cgroup no v1 equals all, which you will need if you do that, which disables all of the old cgroup v1 controllers. Yes, if you do not have systemd or your init system won't do it for you, this is how you can manually mount it, but be warned, you're probably going into like your warranty is void land. So yes. So this is like the go forth and be bold version, but if you have the opportunity, please do the top two. So yes, who's working on cgroup-v2 at Facebook? Facebook kernel team is working on upstreaming improvements and new features. They're working very hard on it, like you'll see them on the mailing list a lot, submitting a lot of patches. Generally, Tejan, who is like the main developer of cgroup-v2, and Johannes are both working at Facebook, so we're really driving this forwards. The OS team and Web Foundation, which is basically me, plus a few others from operating systems, working on operating system integration and production testing and kind of ironing out bugs which occur in real systems. And Tupperware, which is essentially like our, you can think Kubernetes. It's essentially our internal Kubernetes that does scheduling containerization. And we're working on rolling it out to all container users via that method, slowly. Eventually, it will occur. So if you still have questions, cgroup-v2 has probably the best documentation I've ever seen, and I mean that really, like it's verbose, but not so verbose that you're bored to tears. It's like a good combination of verbose and interesting, which is, I don't know, like you should, like the guy who wrote it is Tejan. Again, like he's the kind of guy who writes a table of content on his fucking emails. It's like it's kind of like verbose, but nicely verbose. I hope he watches this video and likes my comment about his emails. I will be around for questions over pizza, so feel free to come talk to me again. My name is Chris, so you don't have to forget my name. You can remember it right now. And thanks a lot for listening.